And there are some things in the security engineering domain that we will go back and review probably tomorrow. But for now, I think that I've done a very good job of touching on the things that you're more than likely going to see on the exam. So we're going to move to the next domain, and that's communications and network security domain. And between these two, they are the security engineering domain and the communications and networking domain, network security domain. There's a lot of information between these two domains. So it's important that we make sure that everybody is on the same page. So if you have questions, be sure to stop me, and I'll be more than happy to try to see if I can answer. One thing that I like to say is that each day I feel like I want to try to learn something new, and for me, that's kind of personally, this is kind of my mantra. That's kind of what life is all about, is to try to figure out something that cranks your tractor, gets you going. And so if there's something that you want to add that based off of your experience, please chime in. It helps for better dialogue, and people learn better to hear it from multiple sources. So please jump in and help me out. Or if you want to just comment on things, please jump in and help me out there as well. All right, so let's keep on going here with the communication and networking domain. And this is, I think, for a lot of people, this domain is one that they typically either are already excel in, or one that they don't really look forward to. And I say that because there's reasons why people get into the business of cybersecurity. There's reasons why people choose this as a profession. And I think that you're either a network junkie, where you live and breathe everything about networking, or you understand it at a very high level, but you're not an implementation or an expert on implementation. And both of those fit the mold for the 10 miles wide and an inch deep for the CISSP. So when we talk about communications and being able to network things, typically what I like to talk about is something, the way that I was taught this at the University of Florida, and it's stuck with me ever since then. I had a professor who said that networking and network communications is very similar to how we speak to people all over the world. And at that time, being a young whippersnapper, I didn't really understand the context of that. But now I think that at that time he hit the nail on the head. And let me give you an example. Parlez-vous français? Parlez-vous français? ¿Hablas español? Sprechen die Deutsch? Un poquito. Sprechen die Deutsch? Dome arigato? So what I was trying to do there What I was trying to do there is immediately try to establish with you how I am going to communicate. Now, obviously, we use English in this, or at least here for the last few days. Some folks, English is a second language. The native tongue could be some of those that I just mentioned, or a myriad of others that are out there. But when we go in to meet someone, or we're traveling around the world and going into different situations, really we have to be able to have something common, that a common language that we can speak. And because of that, many of the worldwide vernacular or worldwide accepted uses are published by the IEEE. So IEEE typically will publish different ways, as far as networking is concerned, that we can establish communication protocols that will enable us anywhere in the world to expect that if somebody is using this type of technology, then they're adhering to the IEEE standard. Because we don't want all sorts of crazy implementations going on, to have one-off solutions for different problem sets. Because if we did, heaven forbid that somebody that implemented that got injured or left that company, that would be a pretty big deal. Whereas if somebody implements, let's say, a Microsoft network, well, 80% of all corporate America uses Microsoft technology. There's a good chance you're going to be able to find a Microsoft certified professional that helps you with implementation or troubleshooting or something like that. And I use that context here because a lot of times we see different technologies that are used all over. And the Institute of Electrical and Electronics Engineers, the IEEE, publishes these standards to try to define various ways that we can have both connected and wireless communications. And so a lot of these protocols, whether it's 4G or greater than 4G, 5G, we're starting to see come out. The 802.11 spectrum, 802.1x with LAN technology. There's a myriad of different implementations where if we just read some of the guidance that is published, then we should be able to figure things out in a uniform way anywhere in the world that we go about implementing different types of technology. And it's kind of a beautiful thing is once you understand that, hey, I'm not the only person out there that may be struggling with this, maybe I can reach out to some other people that have already done it before, because especially now, there's a good chance that someone has already implemented something and published an article on it that we can go out and try to figure out. So I say that as a lead into this comms and network security to hopefully appease any fear in that it's not rocket science. It's something that is quantifiable, typically, that we can actually have tangible ways. We can touch it. We can sometimes see it and be able to understand how these things work. So I say that because I don't want you to be daunted in trying to understand all these different types of topics out there. So we're going to go in, we're going to talk a little bit about some of the principles. We'll talk about the OSI model, TCP/IP, and how to secure network components. What are some things that we can use for secure communications channels, and how we can prevent different types of attacks from happening on modern day networks. So first and foremost, one of the things that we have to do is we have to talk about that way uniformly that we can begin to communicate. And that's going to start with us talking about this thing called the Open Systems Interconnection, or OSI, reference model. This was adopted and used as more of an abstract framework that operating systems use as well as protocols use. And since then, the process of encapsulation, transmission, and decapsulation has become a de facto standard across the business. That coupled tightly with the TCP/IP stack, transmission control protocol and internet protocol, really makes the glue for any and all things that are networking related. And you can go and do some research and find more historical information about this. But when push comes to shove, an easy way to remember it is that there's 7 layers to the OSI model, and the highest layer is the application layer. The lowest layer is the physical layer. So the levels of sophistication usually are more advanced as you go up the stack to layer 7. So layer 1, it's usually cables or wireless communications. As you move up to the more advanced, usually the applications are configured and they have constrained user interfaces, or they have very specific programmatic ways that they implement things. And so one of the ways that you can remember this is to say, okay, layer 7 is the application layer, layer 6 is the presentation, layer 5 is the session, layer 4 is the transport, 3 the network, 2 the data link, and layer 1 is the physical. Or we can come up with some mnemonic ways that we can actually implement this. And for me, there's a number of different ways that we can implement this mnemonically. One of them is down here at the bottom of the screen, starting from layer 7 down to layer 1. And that is, all people seem to need data processing. So a mnemonic way to remember this, all people seem to need data processing, really makes it a little bit easier for us to remember which layer of the OSI model belongs to a numeric layer from a mnemonic. And I say that because there's all sorts of ways that you can remember this. I hear people remembering it the other way, from layer 1 up to layer 7. And sometimes you hear people remembering it like this right here. Please do, let me capitalize. Actually, you know what? I don't like that color. And I'll bring it up a little bit so everybody can see it. So I'll say, please, so layer 1, please do not throw sausage pizza away. So that's layer 1 to layer 7, moving up the stack right there, up the stack. And so what that means is that we are going from a decapsulation up to being able to use an application or an app on our device to read or make sense of that information. So please do not throw sausage pizza away. Please equates to the physical, data link, do, network, not, transport, throw, sausage, session, pizza, presentation, away, application. So you either remember it from the bottom up or you remember it from the top down. And there's a number of different mnemonic ways that you can remember it. Usually or traditionally, these are 2 of the most popular. So pick a way, learn it, and memorize it. And sometimes you can be sitting in meetings where you hear somebody talking about a layer 3 device, and then you see people kind of wander a little bit, and in the back of their head, they're like, please do not throw sausage pizza away. Trying to count on which layer it is in the OSI model, and you see them kind of counting that as something that they just learned over time. to finally it'll just become second nature to you. From layer 7 down to layer 1, angry platoon sergeants train new dumb privates. That's pretty funny. That's pretty funny. I've never heard that. Never heard that. All right. Let's keep on going here. So, like I said, the data travels down the stack through the process that's called encapsulation. It moves across or gets transmitted over the network and then moves up the stack, the receiving stack, through the process called decapsulation. And with this, you can see that the data is added or appended to on the left-hand side, and then it is stripped off by the right-hand side. So the sender will add from the application, it'll add different information at each layer of the packet as it's moving down the stack and getting encapsulated. Basically, it's like data getting put into an envelope and then pushed across the network, and then when the receiving or server receives it, it'll take that envelope, open it up, and then start taking out each layer of the OSI model accordingly. Probably the best example that I have ever seen explaining this right here was in the movie Ralph Wrecks the Internet, the second one. And you know, in that movie, if you've never seen it, the arcade that they are at ends up getting a new game that needs a wireless router. And Ralph and his partner in crime there figure out how to get out to the wireless router. And it's kind of neat the way that, if you've not seen it, he actually gets into this thing that looks like a pill, and the pill kind of opens up like a Lambo or a Ferrari or something with like a suicide door, and he jumps in the pill, barely fitting. The pill then closes, kind of like the process of encapsulation, and then it gets shot across the network. And then when he reaches his destination, it opens up, and then he gets out. So that was a really neat metaphorically way to portray or describe this encapsulation, transmission, decapsulation in a animated way that I thought was pretty neat. So let's keep on going here. So as the data, I talked about data encapsulation here, as the data moves down the stack, it gets appended to. So each layer of the OSI model will add specific information about each layer to that packet as it traverses the stack. It kind of looks Aztecian, like it's from the Aztecs, if you will, because it's pretty much the pillars, or each block is appended to make kind of like a step in the envelope of all the data that is put together before it's transmitted. When TCP/IP kicks in, then we now start to look at a little bit different suite besides the OSI model. So a lot of times you'll hear people talk about the TCP/IP suite being the application, the transport, the internet, and the link layer, the network layer. And so, you know, different types of protocols happen at different places on the network. And because of that, it just really, if you're using it, I use it, then, you know, things just happen smoothly. I remember, you know, when I was first starting off in the business, there was Novell used to have some products. I think they still do, Lotus Notes, where Novell used to actually use sequence packet exchange, so SPX, and they used to use IPX. And what you had to do is, in order to have Novell networks talk to Windows or Cisco networks, you used to have some sort of bridge device that would enable the IPX network to talk to the IP network. And really, I think if Lotus would have just gotten rid of that and started to move to IP and TCP, they probably would still have a fair share of the marketplace. But since then, nobody's adopted that IPX or sequence packet exchange. Almost everybody in the world does the TCP/IP, and it's something that has just existed for a very long time. So each layer has specific things that happen at each layer, and I have it labeled here for each layer. So at the application layer, things like HTTP. So we use a browser at the application layer. Maybe we're using FTP or GUI for file transfer protocol. Simple network management protocol happens at the application layer. Whereas the presentation layer, you look at it and you think, how does this need to be formatted? And based off of the formatting, usually that's how it's going to be presented. So if it's a text file, it would be in text or ASCII format. If it's PDF, then it's presented via an Adobe PDF or a PDF reader of some kind. Same for the MP4s or other things that we use. Session, things like RPC, remote procedure calls, SQL, NetBIOS, network file system. The transport layer, TCP and UDP, and there is a difference between the two, as well as secure socket exchange, which we'll talk a little bit about tomorrow. In addition, at the network layer, we have IP, ICMP, which is very similar to ping. That's one of the functions of ICMP, Internet Control Messaging Protocol, often used for troubleshooting on networks. We have probably the most familiar to a lot of folks in here is Internet Protocol, but then the second would be Open Shortest Path First, which to me really makes sense. If you've ever used something like a Google Maps or anything that is GPS related, they have those built-in Open Shortest Path First algorithms, and for geography and street maps to find the quickest way to get to a destination from your current destination. In the data link, you have the ARP and the RARP, as well as some others. And then at the physical layer, we have all the wires or the actual communications components. So TCP is a connection-oriented protocol, and it will operate at the higher layers of the OSI model, whereas IP handles all the transmissions and the way that it connects across the internet. Where with TCP, you have this thing that's called the three-way handshake, and it's a SYN, a SYNAC, and an ACK. So the synchronize command, the acknowledge or synchronize and acknowledge command, and then the acknowledge command actually will create the handshake and allows that connection to be made between you and another entity that you're trying to connect to. So the synchronize or send command is sent over, and the server will reply back with a SYNAC. Once that synchronized acknowledgement command is sent back to you, you complete the three-way handshake by sending back the ACK, and then the connection is made. Whereas one of the most popular protocols that's used on the internet nowadays, with Netflix being responsible for nearly 50% of all internet traffic last year, 50%. YouTube makes up a large majority as well. All those are sent over a connectionless protocol called User Datagram Protocol, and it's a fire and forget protocol. Fire and forget. So basically, it's let's just go ahead and stream it. We're going to push it out, 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 push it out. No connections need to be made. We're just going to send it out, send it out, send it out, send it out. And it's basically like a pump. Just keeps on pumping, keeps on pumping, keeps on pumping. no connections need to be made. There's no overhead as far as the connection with the SYN, SYNAC, and ANAC. And in this particular case, most modern online games are using UDP. Most modern streaming services are using UDP. Voice over IP typically will use UDP. And things like DNS and IPTV as well. So keep that in mind as you're going through and learning the different things. TCP, you must make a connection. Usually we'll see that in websites and remote connections to servers like VPNs or things like that. Whereas streaming videos would be pumped over things like UDP. So keep that in mind as you're going through and continuing to learn some of these things. A lot of different network components end up working at various layers of the OSI models. And just to briefly cover it, this is not a CCNA class, but I do want to make sure that we talk about some of these right here. And if you have any chime-ins, feel free to help me out. But essentially, I'm going to do a quick and dirty for you here. If I was to, let me go back here. Hold on. If I go back here and we talk about network hardware, if we talk about network hardware here, and I want to try to, equate different things happening at places on the network, at layer 1 is the stupidest device, and that's going to be something like a hub. Whereas at layer 2 would be something like a switch. So a switch, being at layer 2 here, would be primarily talking from MAC address to MAC address. Okay, so a switch talks MAC address to MAC address, whereas a router would be at layer 3 and would talk from IP to IP address. And that's typically the distinction between the different components, the main components that run on a network. And there is some benefits for running different things on the networks, but at a high level, just know that switches talk MAC address to MAC address, and routers talk IP to IP address typically. Some of the hybrid devices obviously might do a little bit more beefy communications over multiple layers, but for our purposes, that's what we're going to go with. So all sorts of things that can happen to try to secure our network. We're going to jump in to talk a little bit about some different types of firewalls. Things like HBSS or host-based security and endpoint protection, like monitoring for host-based intrusion detection systems can be implemented, as well as different physical devices to try to either hardware implementations or things like door guards or something along those lines as well. Different types of ways that networks will be able to communicate. One is a dedicated circuit, which you may have heard of. For some reason, I always think about back in the black and white photos where you see a bunch of ladies in a switch room that they're going in and taking different plugs and plugging things from here to there to where they essentially are making the circuit by plugging in the cables to specific things and essentially routing the traffic. So you have a dedicated circuit between you and somewhere else. That's going to be a circuit switch. Whereas a packet switch is kind of like it, where you would break it up into chunks and then push each chunk over the network and then the receiving end would receive those chunks and reassemble them based on the packet sequence number that was assigned to each packet. So these are the two different types of switching that we see. One is circuit switch, where it's a dedicated circuit. The other one's packet switched, where it's basically carved up, assigned a sequence number, then pushed across or pumped across the network, received, take that sequence number, reorder it back into the proper order, and then you have the communications accordingly. Now, these are things that happen lickety-split. And most of the time it happens behind the scenes. We don't even have to do anything. Most modern day routing and switching devices are very, very simple to configure. Some of the more advanced Cisco products, you do have to know some Cisco commands for that and have some different types of cables to communicate. But for purposes of this exam, we don't need to jump into any of those details. At a very, very high level, know that the different types of switching are circuit switched and packet switched. Whereas anytime we jump into IP addresses, this is where it starts to get a little confusing for some people. And the way I kind of look at it is it's kind of like your home address or your street address, or if you have an apartment or whatever. It's kind of like your street address, and each specific IP address will be unique enough to get mail delivered right to that specific or unique place from there. So what we typically look at is what type of class is the IP address, and there's various types of classes in IP version 4. And we can talk a little bit about IP version 6. And usually the networks are broken up into what's called a subnet or a subnetwork and in a domain. So if you have a company, you create a domain, people can join the domain, assets can join the domain. Each thing that's on the domain or each node that's on the domain typically will get an IP address. And those IP addresses, based off of network access control, can be put into different VLANs or different subnets, and where we allow certain subnets to talk to other subnets through gateways and being able to allow us to have different portions of that network address that allow us to communicate in between these different domains. So keep that in mind. Now, as we're going through and talking about this, some of the things that you definitely will need to know, or you already should know, are terms like NAT, Network Address Translation, where essentially as a company, you're assigned a public IP address, and only the people on the internet can see that public IP address. It's translated internally to the network address translate, or through the network address translation, to try to obfuscate your internal infrastructure schema, IP schema that you have set up. And based off of that, the network address translation, it also going out will look like it came from one address as well. So you definitely need to know a little bit about network address translations, because IP addresses can be assigned to a corporation, one or many per corporation. But then also we can take that IP address and then break it up into these subnetworks internally any way that we want. So we can have N number of nodes internally. And that really, really is very helpful for us in research and development, or as a corporation grows, you can continually add different IP addresses to the domain. So with network addressing, there are 4 octets or 4 bytes, 32-bit network address. I don't want to confuse anybody. Usually we don't see questions on the how to get a network address from a binary. So trying to take, binary, 32-bit binary address, convert that over to an IP address. That's not something that we see on this exam. Whereas on the CEH, we would see that conversion, or maybe on a Cisco exam, we would see that conversion. And the same is for a some of the other things that may be more difficult. We may not see those on this exam, but I will go into a subnet address because it's very likely that we will see a subnet question on the exam. So hang on to that real quick. For different practical purposes, you may have one question on your exam that talks about the different class of IP address. And there's various classes. There's class A, class B, class C, class D, and I think there's even a class E. Those different addresses end up coming up. Class A would be representative of a IP address that is less than 126. So if you had an IP address that's 126.1.1.1, that would be a class A address. Whereas if you had an IP address that is 190.1.1.1, that would be a class B address. A class C address might be something like 220.1.1.1. And keep that in mind. Each one of these, as we're kind of moving through these, you can see that there's limited amounts of different domains, and based off of the different domains, you can create either a massive amount of host or a very limited amount of host. So keep that in mind as well when you're going through and researching this a little bit further. Some things to think about here before we jump into a little bit of subnetting is a host address of all ones is called a broadcast address. Broadcast address. So if you have an IP address that is set to, the last octet is set to all ones or 255 in most cases, then that's going to send out a broadcast message to the entire network, letting everybody know that, hey, I need you to communicate back to me. I'm sending out a broadcast. So if it's all ones, it's considered a broadcast on the network, whereas a host address of 0 is reserved for the wire. So usually you don't use 0 because typically that is associated for the wire. So 255 or the host address of all ones is reserved for broadcast. Host address of all zeros is reserved for the wire. So if we're just in a layperson's network here, again, I don't want to get too complicated. I know some of you are chomping at the bit here. If I had a 192.168.1.255, that would be, in a simplest form, a broadcast address. If I had a 192.168.1.0, that is reserved for the wire. And so we're not supposed to use these addresses right here. These are reserved IP addresses. And I'll talk about how you get all ones here on the next slide, I believe. So there was a time, we're going to talk about subnets here in a second. There was a time, and I think that there still is a time, that we may end up running out of IP version 4 addresses, which are the class A, B, C, and D that I just talked about. And there's been a push to move to IP version 6, which is 128-bit. and instead of a 32-bit, it's 128-bit. So it gives us significantly more IP addresses to work with, and typically is automatically assigned when the DHCP is assigning an IP version 4. So usually nodes on the network will not only get an IP version 4 address, but they'll also get assigned an IP version 6 address nowadays. All right, so what I want to do is I want to talk a little bit about subnets here and briefly jump into this. All right, so with subnets and subnet mask, this is one that you may end up seeing on the exam. Again, we talked a little bit about the class A, B, and C addresses, and I'd be surprised if you didn't have one question on, given an IP address and then asked what class of IP address that the given IP address is, whether it's A, B, or C. So I would be surprised if you didn't get one of those questions. I'd be surprised if you didn't get a subnet question as well. And what do I mean by that? Well, with subnets and subnet mask, every host on the network can be configured or must be configured with this subnet mask. And usually it aligns with the class A, class B, and class C. So subnet mask is a binary representation, so ones and zeros, and it's a portion that is represented in 32 bits as a subnet address. Because of that, network devices will be able to use subnet mask to tell you which part of the network it needs to deliver the messages to. So let's take a look at this as we're going through and trying to learn this a little bit more in detail. All right, so with most computing, we use 2 to the n. Okay, so 2 to the exponent of n. And with networking, we use 2 to the n. And it's very important that we take a look here at what I'm about to show you if you really want to try to understand some of these different ways that IPs and subnets work. So with 2 to the n, we can begin to put together different representations of numbers based off of 2 to the n. And so what do I mean by that? Well, if I have, let me just see how I'm going to do this. If I go to whoops, shoot. So if I go 2 to 2, and then I do n. If I do something along these, let me do this 2 to the n. Come on now. You know what? That's not working. So I'm just going to draw it because that's, I'm going to try to. All right. So if I have, with my pencil here, I'm going to do pencil. So if I have 2 to the n, right? 2 to the n in our networking example here will be 2 to the 7, 2 to the 6, 2 to the 5, 2 to the 4, 2 to the 3. Just bear with me here while I draw this out. 2 to the 2, 2 to the 1, and 2 to the 0. If I write these out now what I can do is I have 1 octet of my IP address right here. I have 1 octet. And remember, an IP version 4 octet or IP version 4 address is 4 octets or 32 bits. So what does this mean? This means that each one of these is worth something. So a character space inside of each octet is worth something. So the 1 all the way over to the right here is worth 1. 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. 2 to the fourth is 16. 2 to the fifth is 32. And these numbers should look familiar to you. 2 to the sixth is 64. And then 2 to the seventh is 128. So what does that mean exactly? That means that if I have a, if I'm given a binary representation of, shoot, I just deleted that. Can I go back? Nope. All right, so if I'm given a binary representation of that, then I might start to be able to put together the network component. It's funny because this is it's not that advanced, but I'm not struggling with the I'm not struggling with the topic here. It's this damn WebEx software that is playing with me. Stand by 1 second, because I'm just gonna take the stupid right out of this. Right here. I'll bring this bad boy over here, and this is how I'm gonna do it right here. Let's go in here. All right, so what I want to do here is I just want to explain this because I know that when I talked to some people last week, they didn't have a good understanding of this. So remember, I said 2 to the n here, right? 2 to the n is what we're dealing with here. And in this case, I think font, isn't that where I go for that? Superscript. Yeah. 2 to the n. And so what I want to do here is with 2 to the n, I'm going to build that back out one more again, just to show you how we do it. So I'm not sure what's here. So if I come in here and I just start to build out this. So if I have 2 to the 7, 2 to the 6th, 2 to the 5, and I'll go back and fix this in a second. 2 to the 4, 2 to the 3, 2 to the 2, 2 to the 1, and 2 to the 0. Then I know that these are representations of different things that different values within the network that are different IP addresses that I'm getting ready to go in and do. So there we go. Build this out, and then it'll make it real easy. Stick with me. So by doing this, what I'm doing is I'm going to assign numbers or values to each one of these places in the IP address. So I do that with the intent that, come on now. Superscript. So now I have the what I need built out. So everything should be, I don't know if it's going to be smooth now, but what I'll do is, again, if you recall, each position has a value. So 128, 64, 32, 32, and it's basically a half of each one as you kind of push down the stack here to give us what we need for being able to calculate things. So each value here has what is shown up here. 2 to the 7th is 128, 2 to the 0 is 1. Now, why did I take the time to build this out? Well, if I have an IP address that is 192.168 11.10, then this IP address can be converted over to a binary representation. And so I can do that very, very easily by taking each number and decomposing each number. So if I take 192, for instance, and I try to remember that each one of these is 8 bits here. So if I take the IP address and I want to try to figure out what the binary representation is for each octet, that means to me that there's going to be 8 ones or zeros in each one of these different octets. So in totality here, there should be 32 altogether. And let's go ahead and build that out. So if I look at each one of these individually, 192, if I was to come up here and try to build out what 192 would look like, it's kind of like turning the lights on the Christmas tree here. I would need 128 and I would need 64, but these other ones here would all be 0 because immediately what I'm going to do is 128 plus 64 is going to give me 192. So my representation in the binary format of this would be 11000000. That would be my binary representation of 192. So how would I write that? I'd go 11000000. And I could confirm that by going over to my calculator and bringing up the calculator here, going to the programmer and looking at decimal, but taking 192 and looking at the binary of it, it's 11000000. So I took, the first digit is worth 128. Second character here is worth 64. And since that equals 192, 128 plus 64, the rest of them have to be 0 here, the first octet. So this first octet here equals 192. And now what I would do is go to the 168 and try to figure out, what is going to be the dotted decimal, the binary notation for 168. Well, I definitely need the 128. I don't need the 64 because that would be 192. 128 plus 32 is 160. So yeah, let's take that. And now I just need the 8. So now I would do this, and this would be here. This would be here, and this would be here. So my binary representation would be 10101000, or that right there. And then I would continue to build this out. What is 11? It gets easier here for me. So for 11, I don't need the 128, right? I don't need the 64. I don't need the 32. I don't need 16. I do need the 8. 4 would put me at 12, and I would bust. I need 11, not 12, right? So I need 2, and then I need 1. So then my binary representation down here would be 0, 0, 0, 0, 1, 0, 1, 0, or 1, 1. And then this last one here would be 10, would be very similar to what I have here. I don't need the 128, don't need 64, don't need the 32. I need the 8. I don't need the 4. I need the 2, but I don't need this 1. And the binary representation of this one would now be 0, 0, 0, 0, 1, 0, 1, 0. And so an address of 192.168.1.11.10 would be represented in binary format like this right here. So you're probably not going to have to do this right here, where you're going to be having to convert this IP address. But one thing that we usually will see is usually you'll be given a networking problem that is fairly straightforward, where you'll be given an address, and let's change it up a little bit. Let's do 10.10.1.0/24. We're going to keep it nice and simple here, okay? So /24 means it's called this is in what's called the CIDR notation for subnets, and that is the classless inter-domain routing notation for subnets. So that tells us that it's a /24, which is the most common and the default that's assigned for a subnet. Well, what that means is that the first 24 bits are turned on in the subnet address. Okay? So what does that mean? That means if I was to go in and essentially I'm going to copy this and then bring it down here. If I go down here and the first 24, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. If those first 24 are turned on and then the last 8 are turned off, then I now have it in binary format represented to the CIDR notation in subnets here. So if I take each one of these, so I say up here, if I turn each one of these on up here, for each of these octets here, and I was to go through and add 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, what I would get here for this CIDR notation is I would get 255.255.255.0, because each one of these octets has a maximum value of 255. And since they're telling me that, hey, the first 24 of them we got turned on for you, I'm going to go 8, 16, 24, and my subnet address for this CIDR notation would be 255.255.255.0. Okay? So I tell you that because usually what we'll see is we'll see on the exam, they'll give you an address that's like this right here, /19. All right, so let's take a look here at this a little bit further. You can see I kind of built it out for us here on the screen. The /19 puts us here, the first 8, 16, 17, 18, 19. And if it's all on, if all the bits are turned on, it's got to be 255, and then 3 of them here. So 1, 2, 3 equals 224. So /M19 would be 255.255.224.0.